Okay, Ekleen, you are now on stage.
Hey everyone, can everybody hear me? Okay. Need a quick confirmation.
Yeah, we can hear you.
Okay. Um, yeah, I think I'm waiting for my peer to join the talk. Let me just quickly send him a text, but he should be joining any minute. He already texted me if he's finding the link on the email. But I will take a quick start with what we are trying to stab today. Yeah, without wasting any time. So, good morning, everyone. My name is Ekleen Kaur. I'm a software development engineer at AWS. And I'm here with Everton Fraga. He's here on the call, and he's a senior solutions architect. Today, we're going to talk about something that directly affects each and every one of you in this room, and people who truly care about Ethereum's roadmap towards stateless future. To do that, Ethereum is migrating towards Verkle trees, and this is already talked about in the previous years at ECC. So it's an amazing open source code, and yeah, we took a stab at it and wanted to find some performance bottlenecks that we optimized upon. And finally, we invented something new. It's fractional Verkle trees that we'll be talking about in this talk. And it gets us almost 36 times end-to-end speed up in the overall execution. So before I get into it, I will give the mic to Everton as he will talk about the introduction on what we do at AWS.
Hey, how's it going, everybody? We're here speaking from the US. Unfortunately, we couldn't be there. We'd love to. And I work on the global Web3 team at AWS, and our mission is to build solutions and partner with great companies to offer those solutions to Web3 companies and to traditional FSI companies as well. We do believe on the mission of Web3 and decentralization, and we basically are here to support the growth of all the companies that want to do so. Um, we do invest in a lot of projects and programs in this space. So we have startup specific programs for Web3. We have blockchain node a project, so basically open source code that helps you accelerate the deployment of Ethereum nodes and other protocols as well. And we're always kind of growing and looking for opportunities to collaborate and push the user experience forward. So, and this kind of takes us to this presentation where, we're always looking for optimization everywhere, as kind of obsessed about this. And this takes us to this phenomenal presentation by Ekleen.
Yeah. Thank you, Everton. Yeah, a quick introduction. I am based in Bay Area, California. Everton is based in the East Coast. Yeah, we are worked on time differences, but that did not stop the innovation that we bring into this work. I am the founder of the Gator Blockchain Lab at the University of Florida. That gives me a lot of exposure with blockchain developments as open source. And I was also at ETH Denver at the Quantum Summit panel. So our concerns took some air around the ETH Denver around ETH Denver, and that's where we started thinking more about some concrete problems that I will introduce towards this presentation. So quickly start getting started. We are very short on time, so I'll keep this very quick. I would like to introduce since our work is mostly built on Verkle trees, I would like to start an introduction with what is exactly a Verkle tree, because I'm not sure the people in this room how familiar they are with this project. To ground everyone with a quick baseline, meet Alice. She, let's say, runs a light client, a wallet on her phone, and then she wants to verify that bot's DeFi contract actually holds 5 ETH. That's before signing a transaction. So with today's Merkle Patricia try, Alice needs a sibling hash on the path for the Bob's account up to the state root. And that's about 4 kilobytes of witness data per account. Every account she wants to verify adds another kilobyte. So the proof size is actually scales logarithmically. As the Ethereum proof grows, as the Ethereum tree size grows, the proof grows with it. So for 1,000 accounts, that's nearly 4 megabytes and a lot of data. So Verkle trees replace the hash ladder with a polynomial commitment and an inner product argument over the Banderwagon curve. So it's roughly 600 bytes total, regardless of whether Alice is verifying one account or 1,000. So that's big O of 1, constant time verification. So this is what actually makes the stateless Ethereum possible. So instead of requiring one validator to hold the full state, Ethereum clients can verify blocks by only using the witnesses bundled in the block itself. So we are building upon this foundation and offering some improvements. So to define the problem, so let's use Alice again. She upgraded her home validator to use go-verkle. So this is the Verkle trees implementation in Go. And her machine has 32 GB RAM and a fast NVMe, but her processes, she is trying to process the same block you saw on the mainnet, and that's, let's say, between 18 to 19 million. And a single block is 10,000 state updates. That's completely normal mainnet load, but this takes about 550 seconds to process. So Ethereum produces a new block every 12 seconds. Alice's node is 275 times too slow. So this is for a small scale validator that does not have the access to a high power computation or a supercomputer or cannot do a distributed networking parallel load. So to consider this from the lens of a very small scale validator, they are never able to catch up and tend to always fall off the network. So the memory is at a 20 GB peak during the execution runtime when you're processing between blocks, let's say between 18 to 19 million. So the proofs that are coming out are roughly in the sizes of 3 kilobytes, and this is not their article. This is what actually runs today. So this was our analysis from our benchmark tests and our motivation behind this work, because we wanted to bring down the proof size to 1.5 kilobytes. So discussing the approach that we took, we found out 4 distinct problems and performance bottlenecks, each compounding the other. And through that, we could extrapolate a deeper architectural finding underneath all of them. So for the bug one, we'll talk about phantom nodes. That's creation on delete. That's creation on delete account, where we saw a straight tree was silently bloating by 35%. The second was database compaction. The third is memory copy overhead that causes about 30,000 heap allocations per block. And the fourth is a cross-implementation correctness fix that I'll talk about in the subsequent slides. So these 4 gave us some meaningful performance improvements, but our final work, Fractional Verkle Trees, is what summarized our entire findings. So let's jump into the phantom nodes problem. So let's consider a scenario that happens on the mainnet. Bob deploys a contract. It self-destructs in the same transaction, and Alice's node calls delete account on that address that never had a balance. So before our fix, delete account always would call a function get or create stem. That means it would create even an address that never existed. So this would create a phantom node that would still stay in the tree, even though the address balance of that account is set to 0. So upon replaying 1 million mainnet blocks, that comes up to 350,000 of delete account calls and hitting an approximately 35% delete, deleted phantom nodes that still exist in the block storage layer. And that's 11.2 MB of wasted memory and 700 milliseconds of extra commitment computation per 1,000 blocks. So this fix is a single check at the top of a delete account that if the stem doesn't exist, we do return immediately, and that means that no node will be created and no commitment will be computed on top of this deleted node. And that's how we step towards fixing the tree bloat problem. The impact for this work was 100% of our phantom nodes were eliminated. The tree bloat was reduced from the existing current state today by 35%. So this affects all the mainnet workloads. And just once fix saved us 700 milliseconds per 1000 blocks. That's a small number, but compacting it over network wide, that sums up to larger time saved. So our problem too is database compaction. So for this enhancement, I want to bring about two parts of the problem. One was a latent panic that we observed, and the second was a key size problem. So for latent panic, this happens during flushing committed Verkle nodes to level DB after every block verification. So when a Verkle node gets flushed to the disk, its slot in memory is replaced with a hashed node, a sentinel that basically says that my child is on the disk. So each node is keyed by its full Banderwagen curve point. So that's a 32-byte X coordinate and a 32-byte Y coordinate, and that's 64 bytes in total. So before our fix, the hash node implementation was a 0-byte structure, and it would create a deep copy of this structure, and this mechanism would call a child commitment on it. So the reason Alice's node did not crash at insert value at stem when the child commitment was called is because hash node would resolve to a real node before calling the child commitment, and this would just save the network from panicking, but any change in the calling order can cause the network to panic, and this problem needed to be fixed. So we fixed this structurally by implementing the hash node that now carries a 32-byte node reference and a cache commitment pointer. So at the flush time, the commitment is already computed, and the cache pointer, and we fetch the data from the cache value at zero extra cost. So overall, this eliminates about 1 second of hidden input-outer latency that previously attributed to state access overhead. And the key size problem uh, solves uh, solves the memory storage overhead by 50%, as instead of using 64-byte keys, we now use 32-byte keys. The usage of those 32 bytes keys is primarily for SS table Bloom filter, indexing block entries, and then causing exponential usage in the CPU capacity. So this would in turn also save CPU costs because of using a lower byte key, DDB key. And this compaction is roughly saving us 15 to 30% throughput improvement in the database layer for fsync, mem table flushing, and log contention functions. Then talking about our problem tree, are the back to Alice. So here, let's consider when we are verifying a node using Bob's transaction. The proof comes as a flat byte buffer. Under the current Verkle tree code, deserializing each proof extracted three fields. One is a stem, that's 31 bytes static field, and then the X and Y coordinate, that's 32 bytes each. So by allocating new memory and copying each one, this is a total of 95 bytes copied per proof. And then this ran across 10,000 proofs per block means nearly 30,000 heap allocations and 950 kbs of heap churn. So Go's garbage collector sees 2 MB of short-lived objects and triggers 3 collection pauses timed right in the middle of block verification. So deserialization alone is right now costing us 12 millisecond. So our fix was to allocate the buffer once and hand out views into it using reference counted buffers. So we allocate the buffer once when the proof arrives, and then a proof view is a lightweight structure with a pointer and an offset. So using our stem X and Y values sliced from the original buffer, we essentially don't have to copy anymore, and that causes no allocation, and then saves up about 100% of heap churn that is getting consumed. This heap churn impact across 6,000 full nodes, that is roughly 7,200 blocks per day, is 829 GB. And this is 829 GB per node and 13.6 TBs across the network. So that's the memory pressure that was silently degrading every validator's performance on every block that this problem fixes. Our next problem is the, so before I jump into my next problem, I want to define Currently, the go-verkle and rust-verkle implementations don't match the proof verification. So each must produce proof that can be verified by the other client, since Ethereum does believe in a decentralized proof future across multiple Verkle implementations. So the problem was that go-verkle has one stem entry, and uh, during block verification, so it uses a proof of absence construct a structure that proves if my stem is absent from the current state of the Verkle tree that I'm viewing. So so the problem is that other stems that wire entries, when multiple keys share the same proof of absence, these proofs become structurally unverifiable from Rust Verkle because of using a vector instead of a hash map. So for building extension list, this emits two entries. One is this is about 192 bytes. So these both of these two entries are mapped to the same proof of absence, and this in turn is called by a depth extension status function that finally proves if the stem is actually this is a correct proof that is submitted by the prover. So in this scenario, when Bob deploys a contract with 8 storage slots, this has never been written. So we authored the first formal Verkle proof wire format as a part of this fix. That specification defines exactly what each implementation must send and expect. So this class of ambiguity cannot recur. The fix was hash map with automatic deduplication and deterministic sort for canonical outputs to send n other stem entries in the wire format per missing key. So even though the internal representation stays deduplicated, the honest trade-off is still a 35% larger proof, since previously go-verkle concatenated just one stem to proof of absence proof, but now we are breaking down all the missing proof stems to the same proof of absence layer. That means a larger computation over each stem and a 33.5% overall larger proof size. But this is a correctness fix, not an optimization. So it depends upon the developers and Ethereum community to finally adopt or not adopt this proposal. But I believe that the trade-off in the proof size is expected because of wanting cross implementation compatibility, and that's essentially what we wanted to tackle for this problem. This is a small compacted summary of all the optimization trade-offs. I'm going to quickly go over them. For processing time and peak memory and proof size, I still want to talk about them as we talk about Verkle trees, so I will skip that in this slide. We did achieve a 24 times faster deserializations in the problems I just mentioned, and a compaction, a 4 times better DB compaction from our problem 2. So moving forward, with the actual main problem that I wanted to propose, that's we solved today. So the problem we are solving today is for Ethereum's high throughput scaling future with a much larger user base. So a fundamental insight, considering 200 million accounts as a single monolithic structure, we can't process different counts in parallel. They might share an ancestor node, but we can't keep it in cache because it's too many GB, and L3 cache is usually 64 MBs in the current hardware requirements. So you can split the commitment worker across cores, and that's like one global root. So one global root causes this performance bottleneck because everything shares a state. So every update touches the root path, and you cannot parallelize this computation. So the working set never really truly fits in a CPU cache. So updates are serial by design, and coming from a team like Elastic MapReduce at AWS, performance optimization is our core tenet. So I am gonna propose, what if we don't use one giant tree? So fractional Verkle trees is a partition state into 1,000 independent smaller trees called hypertrees, and each tree holds around like 200,000 accounts. So a lightweight Merkle coordinator is using these 200,000 accounts as a small 200 MB structure instead of 20 GB overall memory overhead, and then it is easily capable of fitting at least 32% of this 200 MB structure in an L3 cache today, but this problem is for the future. So we do believe the hardware computations might improve so that the full hypertree can be
Thank you very much for your presentation. Maybe you can add us really, really quick conclusions so we won't get late to our schedule if it's possible for you.
Yeah, definitely. So this is almost at the end of our presentation. I will quickly skip the big breakthrough data structure. Our to share in a quick summary on why we are proposing fractional Verkle trees for combining Merkle trees and Verkle trees together. Our core tenet idea was using one coordinated root as a Merkle node and using hypertrees for as a Verkle tree representation. We did do a soundness and correctness proof on multiple benchmarks that revealed us that using hypertrees, the entire state can be sharded in a single computation in a single laptop instead of sharing it across the network. And we do not need to know the state of other partition. That solves a lot of problem for access time and generating smaller proofs. We achieved an overall proof size of 1.5 kilobytes that we essentially targeted. And we also achieved a faster computation from about 550 seconds to a 15-second proof verification. So this is the high-level achievements of what we did with fractional Verkle trees. The code is already open source and is available in our GitHub repositories. So feel free to take a look at the GitHub repositories. Also a big thanks to Everton because he was always very readily available to review my work and help with guiding the direction for this framework. Also,
thank you very much for your time. Thank you for your great talk. And hopefully we will be here next year. We are really happy to have you here on HCC. So thank you very much. May I have a round of applaudissements for that? Thank you.
Thank you so much, ETC.
Thank
this
you.
really means a lot.
See you next year. Bye-bye.